You and Shaoli, you're ready to go.
Okay, great. Thank you
and
all.
everyone else, I suppose, will mute.
Okay. I'm just gonna provide a little bit of motivation of this is, for me, regarding this is truly a very genuine semi-parametric problem coming from astrostat. And let me see if I can, you guys can see my screen here. There's a one plot with this total NH plot. Can you see it? Okay. Let me see if I can move around. Like, this is from Josh Ingram's slide. Josh is another person working on this problem. And so
Josh should be here, actually.
Oh, Josh is here too?
Yeah.
Josh?
Yes, I am. Hello.
Thank you. I'm stealing your slides, and so you can correct me if I'm wrong here. So the problem is let me again, Vinay, you could correct me that I'm sure I won't say everything correctly. What you're seeing here is a distribution of the observed number of flares on the sun flares, and as distributed as the axis side is the total NH. So it's like how many, this is density, like how many flares you see at that NH level. Now, Vinay will tell you that if not due to any kinds of missing data or observation difficulty, what you should see is this distribution should follow a power law. So basically, you will see a lot more, lower NH flares than the high NH flares, and they go down. There's a power law. Essentially, if you look at this line part, there's this between these two red lines, you see there's this kind of follows a power law. The reason you don't see that before the power law is because a lot of the flares that you don't get to see them. So it's a missing data problem. The missing data problem is that, let's say, if you have lots of very low energy flares, they don't get observed. Either they're too fainted or they're because of other high energy flares kind of mask them. And so what Vinay will tell you that what we know is the amount of missingness that goes down as the energy goes up to a certain point, like to this red, which the first red line, where we don't know, we need to estimate where this thing is. Essentially, by that point, you'll be observing practically all the flares. Okay, and then everything will continue to be observed. We'll still follow the power law, but after a while, and I think when they will tell you when things get too high energy, they no longer follow a power law, or at least they don't know. It could be a different power law, or could be something else. So what you have is this very interesting problem where the observer density has three pieces. The first part of the piece is contaminated by the missingness, but they don't know what the missingness mechanism in terms of model. So one way to do this is this part before this the first red line essentially is like a non-parametric estimation problem. But what you don't really care about in the sense that if you know this, if you know the distribution between these, if you know what these two red lines are, you got to estimate the power law. You still have enough data to estimate the power law itself. The parameter of the power law is what's of interest here. That's but they are also interested in where these two boundary points are, like where the power laws start to work, because the missingness, essentially all observations are, all the flares are observed, practically speaking, and to where the power laws stop working, right? So the three parameters of interest here is the two boundary points where the power law actually applies, as well as the power law parameter itself. And before that, after that, are kind of unmodeled. So you got this really kind of an interesting, real, genuine semi-parametric model. There are this kind of a non-parametric before the power law kicks in. Then you have a parametric form. Then afterwards, there's not much data there because it's a very high energy. But it's still, I think, you still want to know what the distribution is, right? If we can estimate it.
It might have physically interesting implications.
Right. Okay, so here is an interesting problem, right? This is like a 3-segment problem. Now, so initially, when I was asked to look at this problem, I mean, you can try to do the maximum likelihood estimation, and you know you're going to hell out for time because you have a non-parametric part, you have a parametric part, then you have another kind of a non-parametric part. You can try to write this kind of mixed sort of non-parametric parametric likelihood, which itself is not trivial at all. And the other things you have to realize that you're now dealing with is almost like a change point. These are the you know, anytime you change the support, things just gets very complicated. And years ago, when I was a new researcher, when I had a lot more hair, so like 30 years ago, I attended my first IMS New Research Conference, and I heard a talk by another new research. Gosh, what's his name? Xufei, what's his name? I'm having senior moments. Yang something. He's at New York. New York's. What's his name?
Immediately. Let me.
Okay. Anyway, so he gave a talk.
Shaw.
Yeah, Shaw something, right? Right. So he's going to kill me because I know him for these years. Now I forgot his name. He talked about this thing called the maximum product spacing methods, which I never heard of. When I saw it, I said, hey, this thing is so cool, but I just never found a use of it until I saw this problem. I say, we can use this. Okay. So Xufei is going to tell you what the maximum product spacing method is. It may remind you likelihood methods, but it's definitely not a likelihood. What I can say is, as far as I can tell, maximum product spacing is a method that got forgotten, but it's neither likelihood methods, nor Bayes methods, nor frequentist methods, nor design-based methods. It's a really different way of doing things. It has its own really interesting features, but it all has a lot of problems as well. So what the Xufei and I have been doing the last half year is trying to understand the methods. Now we have a real motivating example, which is Xufei. I think Robin, you also helped a lot at the beginning of this project, right? That you did all these, because this actually has a fiducial connection somewhere that, and it had these algorithms. So we actually made this work for this problem. But now what we're trying to do is to say, okay, this method has something really interesting, but how does it compare to MLE? And we'll be discovering lots of very intriguing phenomena, and Xufei is going to report some of those today. Any question for me in terms of understanding how did we come to this point using these methods?
I don't see any. If anyone has, there must be some way to raise your hand or something in this thing, which
or you can just shout. There's not too many people.
Yeah, that is true. Yes.
And also, Vinay, did I do a B- job in terms of describing this astronomy problems, or you?
Oh no, I think it captured everything about it. So I think that's the basic problem. I just want to maybe add that it is not limited to just flares, or counting flares, but it could, there are several other places where we encounter power loss, for example, in photon spectra. And in principle, if we figure out how to correct for instrument sensitivity, that's effective areas and radius precision matrices, we can do fits using this sort of thing too.
I think probably worth mentioning, Vinay, if this is correct. I think before we work on this problem, the way people have been handling it is kind of just eyeball which piece looks like the exponential part, and then I said exponential because on the log scale it becomes exponential. It's a power law. Then just fix then fit the power law. Works reasonably well, and but as we know, that's not eyeball is never a too comfortable methods or confident method. So the job here is we're trying to estimate where the power law lives together with the power law itself, and that makes the problem is just a lot more interesting. And again, I wanted to ask all my staff colleagues, Pierre, Lucas, have you guys seen this kind of problem where you really like a one density, you have non-parametric and parametric all mixed together? That I just have never seen this. So I find this fascinating.
I have maybe one question, and that's it for all. like to make that plot, this is based on a couple of observations, I assume, right?
Josh, you made that plot, right?
I did, yes.
That step function. And so is that, the bigger thing here is there's a time factor involved, right? And what are we assuming about the observations here? Maybe talk about total energy. Is this,
Right, what time
Yeah,
period?
those are not
Bernard,
IID observations, right?
we are assuming that at any given time that at least that the major parameters are not time dependent. You're right. If they are time dependent, if the slope changes with time, or if the bounds change with time, then putting them together is going to be messy.
So when we look at that picture, this is for a particular point in time where we can treat the observations basically as IID.
Yes.
I believe this one was the aggregate. I'm not sure which slide it was. I didn't see when you pulled it up, but
This is
I think it
page
included
5.
all. Page 5. I think that was then the aggregate total energy distribution. So if we take all the flares that occur from, I think it was 1996 to 2019.
Well, no, there are also earlier ones, right? This is the
Yes.
right. This is the early ones. That's your part.
Yeah. But the point though, Bernard, is that your point is well taken that these things seem to change over time. But despite that, if you go look at the aggregate, it is still clear that there is a power law distribution that's still apparent to the eye. How good it is, whether we can test for it, how much, how close to a power law it actually matches. Those things are questions that we could answer in more detail.
And it's also an issue, of course, but Shali, you mentioned maximum likelihood, right? To form the likelihood, you're probably going to take the product, right? You're not going to model it jointly. So in terms of modeling, I think also when you do, I don't know, but the product of maximum spacing, you assume explicitly IID.
That's a good question that we will get to the point. I don't think the maximum spacing itself needs to be assumed their ID, although without the ID assumption, I doubt that's a pivotal quantity. I mean, you can just take that as objective function because it's not likelihood. You can say it is. Right. I mean, that's still kind of valid as an objective function. Gotcha. But it may not be the pivotal quantity. That might be the problem. Okay, so maybe Xufei, we have teased everyone enough about this maximum product spacing. Now we can get to the thing. It's a one-line definition, but it does open up a different way of thinking about estimation and construct compensating tool. So Xufei, let me stop sharing that.
By the way, Shali, do you want to introduce Xufei?
Oh, sure. Xufei was a student at in the stat department, and Xufei, you graduated like 2 years ago. I forgot when graduated.
2 years, a long time ago.
Yeah. A long time ago.
2017.
Okay.
Yes.
And Xufei, like some of my other students, they find Six Sigma is not very interesting, so they join Two Sigma. So that has been working there. But Xufei, has really kept working on this problem, and I really enjoyed working with Xufei. We have been meeting almost every weekend. That's the time that we both can work on things. So we have been working on this problem for a while. We started working on solving the real astronomy problem, which we made a good progress. And Xufei, Roping, and others got involved. And Josh is doing a lot. But now Xufei and I, today's Xufei talk is on the kind of a side project, trying to think about maximum product spacing as a general methodology, particularly because it provides a very natural pivotal quantity for any kinds of problem, which is kind of almost mind-boggling to think about it, that existed. And then trying to think about how to use that compared to MLE. And again, we have been discovering a variety of interesting phenomena. I don't think Xufei will cover everything today, but it will give enough for you to think to make a reasonable comparison. Okay, Xufei, it's all yours.
Sure. Thanks for the introduction. Let me share my screen. Thanks for the opportunity to share my research. Can anyone see my screen and the slides?
Yeah,
yes.
I can see it. Yeah.
Okay, sure. Yeah, thanks for the introduction about why we are working on this maximum product of spacing problem So the topic of today for me is to compare this maximum product of spacing with the maximum likelihood, which we always use in our research, or even like the starting point of our statistics knowledge, and to illustrate their difference and some implications that we can get by a very simple example. Yeah, so first, Shirley has made a good review of what is the application part of this maximum product of spacing. So I will recap what is this maximum product of spacing by a more mathematical form. So suppose we have a lot of observations, x1 to xn. They follow a distribution x0. So here the x0 is the cumulative density function. And suppose that x is bounded by the lower bound L and upper bound U. So actually the lower bound and the upper bound can be the minus infinity and positive infinity. So for a given CDF F, we can define this product of spacing as the following form. So the intuitive part is, so given these observations, we can rank them from the lowest to the maximum by the order statistics. And for each of the CDF, we can define the F of the xi with what is like the cumulative density of that observations. And because we have so many observations, this observation helps us to separate the entire probability space into n+1 spaces, which has the summation as 1. So we can use each of the difference and have the product of them. So this helps us define the product of the spacings. And because we know that the summation of the spacings equals 1, so the product of spacings naturally is maximized if and only if each of the spacing is equally distanced. So this is each of the spacing is 1 over n+1, and the product of spacing is upper bounded from 1 over n+1 to the power of n+1. But this is very interesting because for like likelihood, we never think about there should be a like upper bound, a naturally upper bound for that. But for maximum product of spacing, this upper bound is given by the definition and is defined for any kind of distribution. So to have this maximum product of spacing estimator is to find the CDF F that can maximize the product of spacing functions as defined above. So for another thing to observe is if we think that the observations, they are IID, so the joint distribution of the spacing, they are actually following a directional distribution. This is because given the true CDF, so the true CDF x0 for each of these xi is following a uniform distribution. So the F of the order statistics, they are following the order of like IID uniform distributions. So if we use the spacings, they are following the directional distribution. This is also very interesting because for like likelihood functions, we always use the likelihood. We think that the data follows a certain distribution, but we never think that the likelihood function itself is following some distributions. So then we know that the logarithm of this product of spacing or the product of spacing itself is actually following a known distribution, even though we may not know the distribution exactly mathematically, but we can always know what does the distribution look like by simulations. And then this is actually a pivotal quantity. We can use this pivotal quantity to construct a confidence interval or perform hypothesis testing simply from this definition. And then, so like, for example, we can try to find use this pivotal quantity to define the confidence interval like this. So we know that the C alpha, that is that is the quantiles from this no distribution of the product of spacing, and we find that the F that makes this product of spacing F smaller than this value equals the probability 1 minus alpha. So we can use this to help us find the confidence interval. So a simple example is if the F is parametric distribution, we can use this function to find a confidence interval for our estimation of that parameter.
So
now
Xufei, can you go back to the first slides? I want to give people a little bit of more intuition. Yeah, just stop it right there. So you can see that the methods has a close connection with likelihood, right? But so the two difference here. One is it does not use PDF; it's use CDF. Okay, that creates a lot of computational issues. Okay, because CDF, even with exponential family, with a difference, it's not in closed form. So there's a lot of issues that you see why this is not being used in a popular way. But the beauty of CDF is that it's much more flexible. It does not even require the density exist. Boundary points like this kind of discontinuity, it's not even relevant. I mean, it's part of computation. And you can see how this is used for F as being parametric or parametrized, everything you put there. But the connection with the likelihood method, if you think about, if n gets large, these spacings get smaller and smaller, right? So if you do a Taylor expansion, you will see that it will be the difference between these two capital F will be derivative at the derivative of capital F, which is the fx in say the middle point, and then the spacing itself is only dependent on data. So you can see this would be proportional in the large sample to just the likelihood. So in fact that Shao, now remember his name, Shao and others, they prove that asymptotically you need the regular conditions. This will achieve the same efficiency as MLE. Okay? But the beauty of this thing is now we have a quantity, right? Now we have a quantity which is actually by definition is pivotal. The criteria itself is pivotal if you're assuming the model is correct because fx had to follow the uniform. What we're trying to do, right, because this property is saying that for uniform, as we know for uniform, these spacings, right, they try to be, they got every one of them has expectation is 1 over n plus 1. So what this criterion is trying to do is say, let me choosing f or choosing the theta if it's parameterized to make the spacing looks like as uniform as possible in expectation, and therefore I can get. So you can see how this thing will get you the right answer. So in a way, it's like a generalized moments kind of matching, but it's not a matching any particular moment. It's trying to match through the maximum product spacing, product spacing, trying to match a property of a uniform. Now, a couple points worth mentioning that one thing that I do not see how people explore that as Xufei talked about. Should we go to next slides? The one thing I've been thinking about more generally, and if any of you were interested, I'd love to work with you on this. Why not using this whole property? This whole thing is deliciously, right? So that's a lot more information. There's a joint space saying whatever you're fitting, you want this thing. If the model is correct, this thing is deliciously. We're only using a product of the components of the deliciously. Now, why that is like enough? Is there some kind of sufficiency? Kind of a argument that that's all you need to look at, or there's something else that it's convenient because it's close to likelihood function. But what got me fascinated now I'm thinking about is this is a whole different kinds of criteria. It's very intuitive. Just using the fx had to be uniform, and using this and so this is how we're going to go now. Because you have a pivotal quantity, we can construct any kinds of confidence region, probably not going to be interval.
Charlie, quick question from an astronomer. Yeah. What does pivotal mean?
Oh, pivotal just means that the distribution itself is entirely known, has no any unknown parameters. Like this whole thing is like a deliciously, so you can calculate it. You don't know this quantity itself, but its distribution is known. Like when you do the null hypothesis testing, you want the distribution to be known, so you can calculate p-values. Anytime you have a nuisance parameter, we get ourselves into trouble, right? Then we have to deal with nuisance parameter. When you plug in nuisance parameter, then the distribution is not exactly right. You do asymptotics, like chi-square is not exactly right. For any finite sample, it's not exactly right. But here you have a criteria. As long as you can write down what the F is, it's always exact. It's down to sample size too, right? You still need a 2 to do this. So it's an incredibly powerful tool, but later you will see there's obviously price you pay for having that. But so it's very interesting that for some reason that we have not, I mean, this method was proposed not too long ago, actually. It was, I think, Xufei was in 1980s or 1970s. somewhere.
I think the method was proposed maybe in 1940s, but Shaw has a lot of study of it around 1990s.
I see. Okay, so it's a little bit longer than I thought. But anyway, so that's for statisticians, that once we see a pivotal quantity, we're like a home free, right? Because at least you can simulate it. If you cannot calculate mathematically, it's not hard to simulate a deletion, take a product, and you will get the knowledge distribution as you want. You can get as accurate approximation as you want. Only numerical approximation, not the kind of a nuisance approximation. It's not. It's a fundamental problem you cannot resolve when you have finite sample. But here you can. Okay. But there are prices to be paid, right? Other than the computational. Okay, computational, this is a nightmare, even for exponential family. But hey, competition these days are not a big problem, right? And Pierre can do any computation. Lucas can do any computation, like unbiased computation, right? And everything's there. So.
Can I
sure
quickly comment on actually so I'm here of course because I'm always enjoying listening to Xufei and Shirley, of course, but also because I've come across this maximum product spacings when I worked on minimum distance estimation.
Oh, great.
Yeah, so I was curious to see if there were connections. So there's something called the minimum Kantorovich estimator, that is a parameter estimator that is defined by trying to minimize the distance between the model CDF at theta, so f theta, and the data CDF, right?
Yeah.
And that's very intuitive. You want to be close, in the same way that in the maximum likelihood you do the connection with the data and the model, but intuitively also you can try to minimize the distance defined on CDF.
Yeah. Right.
And somehow, I guess this must also, minimize some sort of distance between the CDF, but it's not very clear because it's not phrased like that. So I was wondering, I don't think that this is exactly the same as minimizing the distance between f theta and f0, but it must be not too far either, right?
Right. No, actually, Xufei, am I right that you actually used this because remember the example we give. The first piece is like, before the boundary start, is like a monotone, there's a unimode distribution. And after the boundary, there's a monotone distribution. I think Xufei used this, what do you call this? There's a convexity and the monotonicity, estimated these densities, exactly as a non-parametric, but with a constraint, it's a unimode, right? And with a constraint it's monotone. So I let Xufei to talk a little bit about that.
Yeah, I think for that part, we have non-parametric fitting for the CDF with the constraint that they are monotonic. The PDF is monotonic increasing or the monotonic decreasing. So this translates to CDF if the CDF is either convex or concave. So we are using to estimate, I think, the minimum convex Hall or the maximum concave Hall on the empirical CDF to estimate the maximum product spacing estimator.
Okay, let's go on then to.
Yeah, sure. Yeah, so because of the computation complexity of this MPS, we are choosing a very simple example. So that can have this MLE and also the MPS both estimated exactly. So we are comparing them on the uniform distribution. So the example is suppose the distribution is a uniform that is with lower bound 0, but the upper bound B0 is unknown. And we try to estimate the upper bound B0. So for the MLE estimator, we know that the estimation for the upper bound is the maximum of the observations, which is following a Bernoulli distribution, I think a Bernoulli distribution with a scale of the B0, and the MPS estimator, because it's estimating the spacing, so it needs additional spacing with the maximum value to the upper bound. So the estimation is n plus 1 divided by n times the maximum of the observation xn. which also follows a scale of the beta distribution. So let's compare these two estimators. So first, we know that the MLE estimator is biased because the estimation is the maximum value, which is by definition always smaller than the true B0. But the MPS estimator is unbiased, which is because it creates additional spacing between the maximum value and also the upper bound. So the mean square error for these two estimators, we can easily see that the MLE estimator, the mean square error is almost twice as much as for this MPS. And for the asymptotic distribution, we use n times the B0 minus the estimation. So the MPS estimator is following an exponential distribution, which is the center as the -1 divided by B0, because the exponential distribution, the mean is 1 over B0, which shows that the asymptotic distribution has mean 0. And for the MLE estimator, it's an exponential distribution with the scale 1 over B0, then this explains why this MLE estimator is almost twice the mean square error as the MPS estimator is coming from that it's not centralized.
The question.
Yeah.
So in this setup, you have only the part which is effectively the power law part, right? I mean, you don't have the part where it falls off on either side. So it's just the central portion.
Yeah. So for this part, we only have the very centralized part that we only have the polar part or the uniform part. We don't have anything beyond the bounds.
So what are you doing about the bounds? I mean, so you're forcing the bounds to be 0 and B0, or are they also trying to be?
Yeah, very good question. So for our setup, we're forcing that the lower bound is known, is 0, and what we are doing is estimating the upper bound.
I see. Okay.
We're just trying to choose a simplest problem. Sure. To make the comparison. So simplest is a uniform on having one boundary is unknown. It's easy to generalize to two boundaries. And the other reason we choose a uniform is that people may or may not realize this. When you estimate the bounds of the support, they usually follow a different kinds of law. Actually, go to the next slide. Because Xufei already showed there, right? First, you notice that the variance goes down as 1 over n squared, not 1 over n, okay? That's usually everything goes down 1 over n, but for this kind of stuff, because it's much easier to estimate the bounds, because the maximum value, because it had to be larger than your maximum observation. So there are more information in the data when goes down. So second, as you can see, when you scale this variance, the difference, it does not go to asymptotical normal, right? It's like I go to kind of exponential distribution. There's actually, Xufei is going to talk about these 3 different kind of called extreme value distribution. They have different laws, and if you think about it, it's kind of also intuitive why, at least for the MLE, why it cannot be uniform, because it's always less than the truth. So you cannot be normal, right? It's no matter how you standardize it. But they have these kind of results. That what I want to emphasize here, this comparison MPS for MLE, it's amazing that the MPS turned out to be unbiased and the mean square error is only half. And this result holds for any n. This is not a asymptotic comparison. So here is an example where the MLE is beaten into mean square error by another methods all the way from n equal to 1 to n equal to infinity, right? Now, we usually know that the n, MLE is the most efficient and so on and so forth. But that's the end of these regular conditions that the normality kicks in. And here's explicit examples, normality does not apply. Central limit theorem does not apply because Pierre's right. This is a great kind of qualifying exam problems for students as well, right? So here's the explicit calculation you can do, and basically says MLE is no good. Well, we'll see whether ML is good or not because there's a subtlety. But at least by mean square error, you have something beats MLE all the way for every single sample size. Is that right? Except n equal to 1. Even n equal to 1 probably worked. It was, 2 or something. So you basically have this property. So that's even that itself is an interest that there is a method out there beats MLE all the way, just because of the central limit theorem, that kind of stuff, the Fisher information, all the stuff are different calculation, right? Calculate Fisher information here is not entirely trivial because it's not a differentiable at the B0. So you have to be careful with all these calculations. So you see. Right. Okay. Go on, Xufei.
Can you bias correct the ML?
The ML, yeah. So MPS essentially in this case is correcting bias in MLE automatically.
Right.
Okay.
Yeah, exactly. So Xiaoli points out because this estimation is different and it doesn't rely on the central limit theorem, so this asymptotic rate and asymptotic distribution looks very different from the what we always use as the normal and also square root of n. And Xiaoli points out that actually there has been studied like there are only 3 types of extreme value distribution. So for here it's like for the asymptotic distribution for this x1 or xn, like the maximum or minimum, there are only 3 types of them. So so people define like the type 1 is called the Gumbel distribution, and when that's the true parent distribution, the tail they decrease exponentially. So like normal distribution. So the asymptotic distribution will look at this form. So the exponential of minus exponential to the minus u. And the second type is called the friendship distribution. So this is when the parent distribution, the tail decrease, that is lower than the exponential, like for a parallel distribution. So the asymptotic distribution will look like an exponential to the power of minus u minus alpha. So this is another type, it's type 3. This will follow the Weilbach distribution, which is when the parent distribution actually is bounded on the right. So like what we have in our example, so if the parent distribution is a uniform distribution, then the maximum or the minimum of them, they will follow the Weilbach distribution, which looks like the exponential of the minus u to the power alpha or something like this. So yeah, this is something that I find quite interesting and quite different from what we always use in the normal distribution asymptotics.
Just one quick. I noticed there's a minor correction for type of 3. Here we talk about is bounded on the right. That's for the x, the maximum. If for the minimum, it had to be bounded on the on the left, because it's a kind of symmetric problem. Okay.
One other quick question about the type 2 error distribution. I mean, you say that it has this Fresher distribution after centering and scaling.
Yes.
But if the parent distribution falls off slower than exponential, like a power law, it is possible that it is not possible to center and scale. What does one do then?
Oh, that's interesting. So you're saying, I mean, all these extreme laws are after proper, centering and the scaling, which is the series that you can always find these centering and the scaling, and usually it's very much like the scaling is very much like to make the variance like 1. That kind of a business. Centering here is a little bit trickier because it's not necessarily on one direction. It's not on both sides, and usually it's on one side. So I think it's always possible to scale them. I think your question is what's the limited distribution if you don't scale them?
Yeah.
Right. Well, but then there is. Let me see if the distribution actually. I mean, you can always write a scale one, then do the transformation, do the linear transformation to to find the original sort of unscaled distribution. Although in the limit, if you're not careful, that could be degenerated, because if you scale by n, if you divide it by n, it's going to be like having having like, variance 0, so it's just like a normal itself. You have to proper scale it, right? Because otherwise, if you don't have the square root of n, the thing will just converge to a single point.
Thank you.
Okay, Xufei, gonna go on.
Okay, continue. So let's then go to the interesting problem of how to estimate the confidence interval with this MPS estimator. So for this uniform example, we can write the logarithm of the product of the spacing as follows. So for each of the parts, so these are the spacings of the data points, and so the later part, this is how we scale the spacing. So the summation of the spacing will be 1. So the distribution of this logarithm product spacing is known. So we can use this as the pivotal quantity to construct this confidence interval. So the confidence interval, they can have the exact coverage, but by simulation, we find this confidence interval is too wide. It's much wider than this maximum likelihood estimations. So we do like conditional version of this product of spacing, because in this product of spacing function, we find that there is a lot of the parts that do not depend on this parameter b, so they only depend on the observation of the xi's. So we remove this like the auxiliary statistics, like the x1 divided by xn, and also the xi plus 1 minus xi divided by xn. They are all the ancillary statistics. So by moving them, we have a simplified product of spacing function looks as follows. Sorry, I need some of the brackets. And so with this function, even though the distribution of it might not be exactly the directional distribution, but we can still use it to construct this confidence interval, because we know that the maximum of xn divided by b, they should follow a beta distribution with n1, and we can define x as this and use y defined by the x to the power of n times 1 minus x, which is the exponential of this log of the product of spacing, and we use the CDF of it to construct the confidence interval. So these details are as follows. So we can find an alpha that is the quantiles for this y distributions, and for each of the alpha the alpha quantile, we can define a y0 star of the quantile number, and for this each of the y star, we can solve 2 of this x1 star and x2 star values that makes this x1 star to the power of n times 1 minus x1 star equals this y star, and also the same for this x2 star, because for this y is a unit mode function of the x, and then we can construct this 1 minus alpha confidence interval with this x1 star and x2 star, and gives us a two-sided confidence interval, that is xn divided by this x1 star and xn divided by this x2 star. Does anyone have any questions for here?
Could I just quickly ask, could you say again why in the previous slide the method was the confidence interval was too wide? Or is it obvious why?
So for this slide, why this is too wide? So for my intuition is because it also contains the variability of each of this x of the spacing. So like x1 to divide by b, and also xi plus 1 minus xy divided by b. So this confidence interval also considers the variability of each of the other spacings. But having this conditioning, we only consider the variability of the last spacing. So that's why the confidence interval is smaller.
But can you just say a little more precisely how much wider the previous one is than this one? Is it like just a...
Yeah, sure. Yeah, we have that show, I think maybe in the next slide for true simulations.
Okay.
Does the conditional one still follow Dirichlet? Or
I think the condition does not follow in the directionally. but we know the exact distribution for we can compute the distribution for this conditional thing. So it's not directionally, but we can still compute it.
Can I ask one more thing? So finding a confidence interval, can I understand it's like profiling, like when we find likelihood-based confidence intervals, you're just profiling the likelihood function, and that's the same thing here, essentially, right? You're looking for all B's that are within the disk of Dirichlet in the method that doesn't work in the previous slide. And then,
Yeah. I think, yeah.
Okay, and in here you make those nice tricks to get to a closed form expression.
Yeah. So here is there is a nice trick we can simplify by this, but we think the nice property of this MPS approach is even if you don't do this trick and you don't do much of the distribution, but you can still have this unconditional confidence interval, which might not be an easy approach for for MLE estimations, because for MLE we will always use because sometimes you also use some tricks to do that confidence interval, but that might not be easy for a lot of the cases when you don't have an exact PDF form or other special prediction statistics. And so for this case, the MLE actually they have a very simple confidence interval because we know the distribution for the xn as the beta distribution. So we can construct this confidence interval as xn and x1 divided by q alpha, with the q alpha as the alpha quantile for the beta distribution. So
the n should have the little parenthesis there. That's the maximum order statistics.
Yeah. That should, yes, they are right. That n should be the order statistics xn, and we find that the length of this confidence interval, so the unconditional MPS is much more larger than the MLE, so it's around 7 times larger when we have 100 observations, and for the conditional ones, the confidence interval is much smaller than the unconditional ones. It's around 3 or 4 times more shorter, but it's still larger than the MLE. I think this reason is for the MLE is depending on this beta distribution, and it's trying to cut the distribution with the highest PDF. So it's having the shortest confidence interval as possible.
So before you get to it, I want to spend a little bit of time to discuss this with particularly my statistical colleagues here. There's a very interesting phenomena here, and Xufei and I were being scratch our head to trying to understand this. Remember, we show you that the MPS as an estimator, not as an interval estimator, as a single point estimator beats MLE all the time into mean square errors, okay? Half of the mean square errors. But when we construct a confidence interval, you can construct a confidence interval, because MLE here, because it's a known, the estimate itself has a known distribution, so you can directly construct confidence interval, which works out very well. The MPS estimate itself, also, because it's just a multiplier of the MLE, you can also construct confidence interval, and it will give you exactly the same confidence interval. So if you just use MPS MLE as a point estimator, they give you exact same confidence interval. Okay, there's no gain, but there's no loss either, right? Okay, so that's first is interesting. Into mean square errors, one does much better than the other, but so that actually says something about my thinking is that says something about what's wrong with the mean square error. Because remember, mean square error is pretty much a symmetric criteria. And in this case, everything should be kind of more like a one-sided. So there's something about the mean square error may or may not be the right criteria, okay? But let's put this aside. Thinking about now, how did we construct the MPS confidence interval using not the point estimator, but using the product spacing criteria, okay? Now using that criteria, it's very general. And then, so the problem is very general, that it'll guarantee the coverage, but achieve the coverage by doing this unconditional one, right? It's much easier to get the coverage unconditional than conditional, most time, because you can average more stuff. You can average things out. But there is a conditional version, which is essentially we borrowed from the classical notion that anytime you do likelihood inference, you should condition on ancillarity. I know Lucas is going to jump on me because we had this discussion about all the other stuff, but at least in these classical problems, you should condition on the ancillarity. Now, should we go back to two slides before? I want to show you where this, to answer Lucas the points here. Go back a little bit more to this previous slides. Right, Lucas, now look at the middle part, right? Because you have these log of the data part, because the log of data part, the first two, log x1, the log spacing, they don't do anything because there's no b involved, right? In the likelihood method, you will be throwing them out, right? Because they don't, by adding them, in terms of confidence coverage, it doesn't care. It basically it creates more variability for you to cover things. So you can do, the coverage will be exactly right because the theory tells you so. But you can see that you're adding these ancillary statistics. They're not relevant. They don't really have information about the B itself. So what we did is, so when I saw this, I said, Xufei, let's invoke the conditional ancillarity principle, even when doing maximum product spacing. So we did that. And I was hoping by condition on that, I would recover just like the MLE. It doesn't. Well, the reason it doesn't is because, if you go to the next slides, you will see there is this kind of the awkwardness. You see the B, the X and B, it was using these two parts. They actually create this kind of redundancy in this distribution. You could have just using Xn itself to construct confidence interval, and that will give you the best one, as far as we know, just like MLE. But if you use this criteria, it's a function of Xn, but it's not a monotone function. And this non-monotoneness creates this kind of unnecessary kind of folding. You still keep the coverage right, but you pay a price. And the price is not trivial. If go to the next slide, trivial. Right. So you see the price you are paying is not trivial. Essentially is like a 30% or more width. Right? It's almost exact 30%. I think there must be a theory you can calculate. So this leads to multiple questions here, but this is just a kind of a toy example, right? We see that as a point estimator, the maximum product spacing does well, recover unbiasedness, and it does a half a mean square error. It's great. As a constructed confidence interval, it didn't improve anything. It didn't destroy anything. But if we use the product spacing itself as the criteria to construct confidence interval, the beauty of it, it's a universal recipe. I saw, Lucas, your point of when things are discontinuous. Discontinuous is going to be a little bit complicated, but I do think there's still cases that will be pivotal as well. Because you can define these inverse CDF in a way that things may still work out. I'm not entirely sure, but the continuous case is kind of trivial because it's a uniform. Otherwise, it depends on where this discontinuity point is. It may still be a pivotal quantity, but it may or may not be the kind of a deletionally. Now, the conditional distribution, you can always do it. You should always condition ancillarity. Now, itself needs some proof because we're no longer talking about likelihood inference. We're talking about product spacing inference. It does seem to achieve greatly that reduction. But the intriguing part is it doesn't go all the way. So the question is, what are we losing here, right? Like, what is the principle? What are the conditioning principle in the product spacing case? It will recover like just using the point estimate. Is that possible? And in general, how do you do the conditioning? And what's the trade-off? The one thing, as Bernard already noticed, when we do conditioning, it's no longer deletionally. It will be the deletionally conditioned on some margins, some function of that. So again, it's a well-known distribution in the sense you can simulate it. You can even do numerical calculation, maybe even do theoretical approximations. There's no nuisance parameter involved. So that's the beauty of it. It opens the door for all kinds of exact calculation up to the numerical accuracy. But for me, the most interesting part here is we do have a method to construct confidence interval, parametric and non-parametric in general, but you're paying a price. The question then here is, like in this problem, I don't even know what's the best confidence interval. Is the one based on MLE is the best confidence interval? I cannot vouch for it because I know even as a point estimator, I already have MPSvML. But is there something even better than that, Lucas? That you have questions?
Yeah, just in the previous slide, is the conditional MPS confidence interval, it's equal tailed, right?
Did we make it equal tail? I mean, there's a choice here. No, I don't think it was.
You mean equal tail means
is that equal tail? No, I don't think it's equal tail.
Centered? I don't think so.
I don't think it's equal tail.
I mean, unless
no,
one star is 1.
Yeah, I think it's not equal tail. It's not.
So how do you choose x1 star? And is it 1? Because if it's not 1, then it's got some left tail, whereas the other one has no left tail, right? Because you're using xn as the left endpoint.
Right.
So it seems like maybe they're not really comparable necessarily. You could make x1 star equal to 1 and then see what x2 star you get. And it seems like that's the one you should be comparing because that is the same left tail.
But I don't think we actually got to choose x1, x star by ourselves, right? It had to be solved by this equation. They both said there are 2 equations. So there's a unique answer to it, right? Other than maybe, right? So x1, x stars are given by this, there are 2 equations.
They are given by the equation. The x to the power n times 1 minus x should be equal to y star, and y star is the quantile from the distribution. So the product of this beta, but we can solve this x1 star, x2 star exactly, and plug in them here to get this confidence interval.
I see. But this does imply a particular set of tails, whereas you've also made a choice for the MLE confidence interval that you are going to have 0 left tail. Could you just change that choice? What if you did an equal tailed interval? Would it still be much better?
Interesting.
I suspect things get much worse because it's exponentially distributed. The 0 left tail, I think, is the best choice, right? Because that's where you have like the most mass. And you always want to pick an interval that maximizes the density inside it.
Right. Yes, because that intuition is correct. But on the other hand, right, you would almost think like, because we know the left tailness is saying, because we know the B had to be larger than xn, right? But on one hand, that's great, it's guaranteed. On the other hand, you're being too conservative. You almost want the x1 star a little bit less than 1. You want to say like, because it's a probabilistic bound, right?
No, well, it depends on what tails you want. If you want to minimize the width, you know that you want the left one to be exactly 1, right?
Correct. So the question then is, what's the correct criteria here, right? You're right, because the mass there, and
I guess another way of putting it is in the next slide, you're comparing two confidence interval procedures. So the second one has 0 degrees of freedom, whereas the third one has a degree of freedom, which is you get to choose how you divide the tails between the 2 sides. And you've picked the best one.
Yeah.
So it's like not clear to me. I don't know exactly what it means that like one beats the other, because the third one has a degree of freedom that you get to choose. And by optimizing it, it's better.
Yeah, but that's in a way saying that MLE is more powerful, right? I mean, not necessarily MLE, it's a point estimator. Because I mean, the goal here is say, okay, let's say the goal here is say we want the exact coverage, which all of them achieve exact coverage, and then we want the interval as short as possible. Let's say that's our optimal criteria. The question is that we have MLE to get that, at least so far. We don't know, is there some other method beats MLE? I don't know. Right, because now I lost trust of whether MLE it's the best one here, but MPS doesn't do better, and it's kind of interesting. The MPS the criteria was able to lead to a point estimator does better, at least the automatic correct bias get the smart mean square error, but the criteria doesn't lead to a confidence interval. Maybe we haven't done the right thing yet. We did a conditioning, which is already far better than not conditioning, but maybe there are other things we can do. The general research question then is, what are the other things? Like, how do we think about this, right? And
can I ask something?
Yeah, go ahead.
So, in that sort of comparison with the MLE, I was wondering if you considered a problem where the MLE would not converge, for instance, Cauchy data and normal model.
Mm-hmm.
But this thing with the maximum spacing, that might still work somehow.
Yes, I know what you mean. Yes, we have not tried those things yet, and yeah, I mean, I think I'm quite sure that we will find examples that MPS will beat MLE. But the question then is like, now are these generally competing methods, right? When one does better, one the other bad? I mean, that's kind of all the general, general questions. Because the one beauty of this thing, as I just said, you may use ML, you cannot even find exact coverage, right? And here you can always find exact coverage. Now, it may be a useless interval or a useless region. And also, if you have a nuisance parameter, this MPS is going to come with a join region, right? Because we don't know how to marginalize things yet, because MPS only guarantees you do the join, join coverage. There might be some clever conditioning allow you to profile, right? That kind of stuff as well. But it's just and the question for me, the interest here is like, okay, here's another method guaranteed to have the right coverage. And the question is how much we can push and how does it compare to MLE? And even for the simple uniform example, it's already more nuanced than I expected. Initially, when I say the point estimate beats MLE, I would say, oh, great. Like this might just beat MLE all the way. No, it doesn't. And so, like, look at the criteria itself. Is there some other ways of conditioning? Is there? I mean, conditional ancillarity was based on the likelihood principle, right? It's not based on the product spacing itself. I mean, the other thing I've been thinking about, slightly sidetracking, I was wondering whether maximum product spacing itself is a likelihood, but based on like interval data or some other, right? Because it could be just because in the end that is it's like these partial likelihood can be viewed as a likelihood of partial data, right? And maybe this is like I don't know, because these intervals are not you see, our initial sort of was just simply it's a probability within each interval, but these intervals are not independent of each other, right? Because these are the uniform intervals. So therefore, the product form does not make sense, right? If you think about if we really want to do that taking the interval as kind of the data, then it's not this kind of simple product space. So that might be another way of thinking about, but I don't have the answer yet. So
can I ask a question?
Sure.
This is probably a stupid question. When you say you were conditioning on the data, I think it's the previous slide. Did you remove those bits that does not involve B, or did you set them to the value as they were observed?
Okay, go back to the slide.
Right here. So it says that removing the components depend only on data.
Well, what we did is take the previous criteria. We do the conditional calculation conditioning on this quantity, which effectively removed the constant part, right?
So you set that to 0.
No, you don't have to set that 0, because if it's conditional on that constant, when you do the criteria, it appears on both sides, right? Become a constant. It's like A plus C less than some criteria plus C.
So wait, I don't quite see.
Okay, go back to the previous slide. That's most important. Okay, yeah, just look at this, right? So when we say we did the conditioning, what it was removing is take a LPSB, right? Now you calculate its pivotal because it has a distribution, right? Let's say we want LPB less than some constant, but the probability of the less than constant equal to 1 minus alpha. But except that we do the constant calculations conditioning on that ancillary statistics, which means by conditioning on means like anything only involved ancillary statistics become constant. But the rest of calculation is becomes the xn, the maximum order statistics, conditioning on that quantity. So it's a different calculation.
Because, so I'm just comparing this LPSB definition on this page and the next page.
Right. Yeah, that's a little bit confusing because it's actually because now this be conditional on that ancillary statistics. This is a constant of the previous one, different by the previous one by only a constant term.
So is it that the part that you say that depend only on data, do they add up to a certain thing? Is that what definitely happens?
No, because if go back to the previous slides, Because if you divide everything divide the first two terms by xn, and then you're adding that xn to the rest of them, then the first part will be just the constant you're conditioned on. You just rescale everything by divide by the xn. Right, so you minus log xn plus log xn, so the thing is still entire balanced, and then the first part, like the one in the second line, that becomes just a constant.
Oh, I see.
Just a constant, yeah. So that's what we did. But so it's not just removing. Now, okay, you actually remind me something. That's interesting thought. You could do the removing without conditioning. But that doesn't get you. Xufei, actually, now I want to ask you, Xufei, like you did the calculation, right? You could do the removing without conditioning. So the xn still follow the beta distribution, not the conditional beta distribution. Actually, Xufei, I think that's actually not right calculation here. Now I just realized, right? Because maybe that's the puzzle. Because xn over b here is no longer the beta. Condition on that thing is not a beta. It's a complicated quantity. Maybe the reason we didn't get the right answer is we didn't do the conditioning. We did the removing, which is different from conditioning. You see what I'm saying? Because the xn no longer has the beta distribution, conditioning on this sum.
I think here is a special case. Conditionally on the other part is still a beta.
It's still beta. I see. Because independence.
Yeah, I think so. Yeah, I think.
Oh.
Yeah, I think we did some calculation and this is special. Okay. So even conditioning is still beta.
Oh, okay. Yeah. Sorry. You're right. That's because I know why that's because the Basu theory, right? Because the ancillarity is invariant to because because it's the sufficient. That's how does the Basu theory works?
Ancillary and sufficient statistics are independent.
And xn here is sufficient for B.
Yeah.
Therefore, okay. So you're right. So in this case, it's simply just removing because of independence.
Yeah, but I think what you mentioned is right. So maybe removing and conditioning, they might be different in some other cases. So here is a very special case where they are equivalent.
Yeah, because they're independent. Yeah. You're right. Sorry, Xufei, I forgot. Yeah, we did have this discussion. Yeah. I mean, it's cool, right? You need to use the Basu theorem. How often do you use that? So
I guess a related question to that is, how did you find these set of ancillary statistics, and how do you know this is all there is to it?
That's a good question. Although, I mean, by inspection, you will see once you remove that, there's nothing left. There's only xn, right? Xn is sufficient. It's not an argument. It's not a rigorous proof, but we have removed out the maximum. We have removed out everything else, right? The only thing left was xn. It had to depend on xn because xn itself is sufficient for B. And that quantity itself is obviously invariant to B because it's a scale invariant. So that's why that's ancillarity, right? You're asking whether that's a maximal ancillarity. I think it is maximal ancillarity, but we also know maximal ancillarity is not unique. So I'm not sure if this probably is not unique. Although it's hard to think about anything else in this case that is not. The problem is, you see what happened was you end up with a criteria is not monotone in xn, and the likelihood is right, Xufei. I think the likelihood function itself is monotone.
Yeah. I think besides that, it's not monotonic in xn guarantees that what we get as the MPS estimator is always included in this confidence interval. because it's not monotone for xn, so the value that maximizes it is not xn, is like n plus 1 divided n times this xn. So it's
I see.
So it's consistent with the entire MPS estimation, so it
Yes.
doesn't break the estimation. So maybe that's the price we pay for the larger confidence interval.
Bless you. Yeah, it's very intriguing, right? When we look at this expression, I say, we got it. We got down to, but then we realize that it's not a monotone. It's not monotone. Then you have this folding problem.
Yeah.
And you pay a price.
But this must not happen in general, right? Like, it seems to me like if you were in a problem with more regularity conditions, where you were maximizing something with a second derivative, then shouldn't everything kind of work out nicely? Because if the asymptotic distribution because I think the asymptotic distribution of your maximizer should be intimately related to the second derivative of the function. And your asymptotic distribution, which we know the MPS is efficient, that means that basically you should get the same asymptotic confidence interval for both of them, no matter what you do. If you have regularity conditions, which you don't have here.
I completely agree. I think that your intuition right, and but on the other hand, it's more interesting. Yes, I mean in that case, people say, why bother? I mean, I guess you still can do the finite. You still have a benefit of doing finite sample exact thing.
That's pretty nice, right? That's pretty nice. That's pretty nice, right? It's finite sample exact, and it's asymptotically efficient. Both the inference and the estimator, right?
Right. So but of course the price you pay is the computation is a lot harder, like even for exponential family, right? Because you look at a CDF, you switch into integration, and you look at difference. There's no sufficient reduction. But hey, it's my hunch here is I think that this is actually very much related. The whole maximum product spacing, looking at these intervals, I think it's very related to these, what do you call these, the conformatory prediction kind of problem. Because all you're doing is trying to utilizing this thing is kind of a permutation, 1 over n. Like everything is uniform spacing. I think that's kind of a thing why you can get these kind of exact. It's just in a more modular base. This whole dilution essentially gives you everything, right? The dilution tells you everything. Like all the information you have is in this spacing. If you buy the spacings, right? There's that's the one thing. Yeah, but you're right. So that's the so maybe. But on the other hand, the reason we got into this is because of these boundary points, right? You will see that the MPS that handling these boundary points is just a little bit easier because you're dealing with CDF. I mean, when we did it, the calculation is just I don't even have to worry about whether the thing is differentiable at these points or not, as long as it's continuous, which is continuous in our applications. And but you're right. So there's seems to be explored where maybe it's with the help of computation is a kind of win-win situation. You get you have asymptotic efficiency, you have the finite right coverage. Although what I'm not sure, just knowing this problem, even this is kind of an unusual problem, whether you still should have invoked the conditioning on the ancillarity.
Well, it doesn't matter whether you invoke it or not, right? Because it's independent.
No. In this case, it's independent. I'm saying in the more general case, like do you want to? I mean, for the finite exactness, whether you need to conditioning on the ancillary for the more complicated problem, which is again the trade-off for computation and the kind of a volume that you end up with. By the way, this will also give you a great way to the hypothesis testing, right? Because you always have a knowledge distribution right there. Okay, you can test. I mean, it may be terribly, not powerful test, but it will be a valid test. So.
Can I ask also, is this a way of estimating the KL divergence? Possibly.
KL divergence.
I mean, if it's asymptotically minimizing the KL divergence, but it has better finite sample properties. Maybe it's sort of connected to a better way of estimating the KL.
I see. That's an interesting point. I haven't thought about. And yeah, then it's not just KL, right? Any other distances if you want. All the F divergence, the kind of distance you can. Yeah, it's certainly possible. I mean, more broadly, what this whole thing reminds me is just like, it's a very simple idea, right? Use the uniform property of fx, whatever you model for that, right? That's the grand idea here. I mean, this is just one way to use it, and somehow we, that right there, it's a by definition of a pivotal. Other than the continuity issue, we can look into that later, and so there opens up a lot of things you can try if you care about this exactness.
So I have a question for Xufei. So this comparison of the intervals that you have in the table, these are when you say simulation, I mean, did you run the MPS algorithm to estimate these things, or was it just that you generated a bunch of data sets and calculated the exact intervals in all cases?
I think my simulation, I just simply generate a lot of uniform and fix the maximum value and use the two formulas. For the ML, I use the maximum xn and x1 divided by this qa, and for the MPS, I use this xn divided by this x1 star and x2 star. I can, for the same sample size n, I can compute this x1 star and x2 star almost exactly. So I'm just computing them.
So I was just wondering if it's consistent then with the with how the what's it called, the QQ plots. I mean, do they match up properly? For example, I mean, you remember that in the when we look at the actual data, there appears to be a bias in the estimates, right? So I was just wondering if that is an algorithmic or coding issue or something that's coming through because you're not looking at the uniform versus tilted distributions.
I see. Yeah, I see. I think for this simple example, I didn't compare with the other QQ plot. I just generate like ID data, so I don't have this data like inconsistency or time issue. So yeah, I didn't do that. Okay. So is there any other questions? Yeah, sure.
Yeah, go ahead. Sorry. I was just going to say that we have like 5 minutes left.
Yeah. So we'll talk about some future works that could be derived for this very interesting problem. So we like to study like how to construct this confidence interval for like more general problems, and also to better understand how to carry out the ancillary conditioning principle for this MPS approach, as we know that this unconditional MPS approach might be too conservative. And also we might want to have like theoretical insights on why this MPS can do better than MLE for the point estimators, but not for this interval estimation. Did you have any other questions?
I have one question, if I may, on I still don't quite understand why the unconditional confidence interval isn't performing well. There's no asymptotics involved, and there's not discreteness involved. So shouldn't the coverage rate be perfect? I don't.
I think the coverage, they are the same, but just the interval, they are like, because as we mentioned, the interval, we could have like different centers, and with the same center, we can have different tails. So the unconditional one, that should have a very longer tail that makes it larger. And besides, for my intuition, why the unconditional one is not doing well, is like from this functioning, is also considering the variability of this x1 to this 1, x2 to n minus 1, but for the conditional ones, we think this is known, so we didn't consider the variability from that side that helps make the interval smaller.
Yeah, here the issue is not the coverage. The coverage are all exact. Is the is the interval length, and
I see. Yeah,
interval length is they're too wide. I mean, in general, you can see, right? Because the whole thing is trying to get the right coverage. Now, right coverage you can think about have different replications, whether it's conditional or unconditional. And in general, the unconditional ones are easier to get the coverage right because you just get the average more stuff. If I mix it somewhere, I compensate somewhere else. The conditional coverage is harder. Right? So this MPS method, the product spacing method, provides a general recipe. Say, I can always get you the right coverage, but the price you may pay that it actually may do something really crazy, right? We might come up with even regions probably will including like infinity, like a half lines, all the stuff. But it is cool. It's a generic way to start with something. Then you can try to say, okay, now I can make the better, the conditioning. If we condition ancillarity, we still guarantee the coverage. The computation is harder. So that's the kind of that's kind of the trade-off here.
Okay, but you're claiming that the conditional coverage is also exact.
Conditional is exact. Yeah, exact to a point of numerical calculation.
Okay.
Or theoretically we can do that. I mean, there is in this case actually it's not even numerical because the ancillary condition turn out to be independent,
right.
And all it does is just remove this additive constant. And but you can see that additive constant itself in the unconditional version, it's not a constant. It's varied by itself. You can see how the quantity depends on what the sample you have could make the interval really wide or smaller. By eliminating that, then the thing is just much more concentrated. Yeah. You're thinking about it's like doing regression, adding a bunch of unrelated covariance. It doesn't change your unbiasedness, but it makes your estimated much more wider. The variances. That's essentially the same analogy here.
Like you could see if the minimum is really badly estimated, that could throw off the entire thing.
Yeah, exactly. Right. Yeah, exactly. So, yeah. But it's interesting is that by conditional ancillarity, the criteria itself doesn't go all the way to the MLE. Has this additional price we're paying, which we don't quite understand yet. And I think Lucas is right because this is a kind of an unusual problem. But it is. But it's unusual, but on the other hand, this is the only problem we know that the MPS is in closed form. Because you just calculate everything, you don't need the space in the middle, just everything. So you can do these calculations. Every other calculations, we don't know how to, we have not looked hard about it. Xufei, if we have boundary points on both sides, do we get a closed form? Like if we have A and B?
Yeah, I think for boundary, yeah, we still have closed form. Yeah, we still have closed form.
I see.
And for that one, the confidence region is a little bit complicated. So I choose this one bounded one, so we can illustrate this both the point estimation and the confidence interval exactly and very clear.
I see. Any other questions?
Can I do one more last thought because it's so interesting?
Yeah.
So because, like we mentioned, F continuous. So what happens with discrete data? Like even if you consider the discrete uniform, it's just one upper bound. Does this translate?
I mean, you can still do the calculation. The question is, what is the pivotal quantity?
The joint distribution, right? Yeah. Because you were asking once, right, is it similar to maximum likelihood? It would be interesting to see if for discrete data, this is closer to the likelihood or not, the product of spacings.
Yeah, I think that's
if you have ordinal data, I just don't know if you have thought about that.
Yeah, I haven't think about that, but it's quite interesting for discrete data. Yeah, how is the spacing defined for them? Yeah, so that's. But I think that could be very close to the MPS, the PMF, because the spacing is maybe the cumulative PMF. That could be quite related. but I haven't think about it very carefully.
Yeah, well, there's a lot to do and lots of things to think about, but you can see why Xufei and I will be having fun over the weekend. I mean, this is like as classic statistic as you get, but still there are so many open questions. And amazingly, that is all thanks to Vinay that brought us this interesting problem to make this thing live again.
Yeah, trying to. I mean, it took me a long time to convince people that this is actually an issue, but.
Yeah. All right. We would love to hear you guys' feedback and a question. We already have a bunch of questions. There is a lot of interesting stuff here and thoughts. There are lots of interesting calculations. For example, as far as we know, that nobody has calculated what is the distribution of the product of the component of deletion length. Like that's a known distribution, right? Okay, so that should have a name of the distribution. It should have a closed form. It may not be closed form, but it's a one-dimensional distribution. It could be tabulated. So right there, you have something, and it's being important because that would be the default distribution for doing any kinds of testing. Then of course the conditional version is getting more complicated. I don't know. I don't know what the distribution looks like, other than it's a bounded one because it has a bounds. But does it have a bound? Yeah, it has a bound because the sum equal to 1. Yeah.
Yeah.
So it's is it, right. So right there should be an interesting calculation. It shouldn't be that hard, and Josh can do it in 3 minutes by simulation. Josh, right?
Oh,
of course. Give me a minute and a half.
The other minute half is to write it up, right?
All right, so I think we've reached the end of our scheduled time.
Okay.
So thank you everyone who joined. I'm going to, I guess, Xufei, if you have a few more minutes, maybe we can stick around and chat
Sure.
with those who are
For
interested.
those of us, yeah, maybe we should chat.
Sure.
I'm going to stop the recording now.
Okay. Thanks to everyone to
Thanks.
join us.
Thank you, Xu.